Okay, we are recording. All right. So I have the chat up if you do have questions. And my goal with this, you can write down the goal if you want to, but it's just how to write explicit and recursive equations. Should be an S there, for linear and exponential. Okay, yesterday we covered the explicit. We started remembering from last year. Someone said, I think I understand this really well now. That made me feel good. But today we got to talk about the recursive ones. So as some people are like writing down the goal, and definitely write down the table that I have here, okay? How many of you guys remember recursive from last year? How many people remember how to write recursive equations? Anybody? Probably not going to get many yeses here, but does anybody remember recursive from last year? Okay, I see 1, I see 2, I see 3, 4. All right, that's good. Stay with me anyway, okay? For the rest of you guys, really make sure that you listen close to this because it's just the notation that's weird, okay? It's not a hard concept, not a hard concept at all. It's just like the code of it and the way to write it is strange, okay? Okay, so first of all, my little purple table over there, let's write an explicit equation for it. Is it linear or is it exponential? My little table over on the side there. Which one is it? It is, someone says, it is linear, right? So I'm going to write that in. It's linear because it's adding, right? Plus 3, plus 3, plus 3, plus 3. Okay, so that means it's y equals mx plus b. And m is 3 because whatever changes is m. All right, so I know that m is equal to 3. And now we need b, okay? B is the y-intercept. What's the y-intercept? It's what's across from 0 in the table. Oh, but there is no 0 in the table. No worries, right? We work backwards. And what would go right there? If I worked backwards, what number would go across
4
from 0? So it's adding 3. So this would go down 3 to 4. And 4 is across from 1. But then if I go down another 3, what's across from 0?
1.
1. Yeah. So m is 3. My b is 1. And I'm going to write y equals 3x plus 1. And if you write f of x equals 3x plus 1, I like that even more. Okay. Questions on that? Would you hit the green button if you understand that? How many people understand how it's 3x plus 1? Hit the green button. The more I see, the more I know I can be quiet. Okay. Yeah. Okay. Now it's time to do the recursive formula. Okay. So a recursive formula, in the video, he gives a pretty good definition of it. Like I do like the definition that the guy gives. So hold on just a second here. So I maneuver a few things here. Okay. Hold on. Okay, here's the video again. You can watch it later on your own if you want. But okay, guys, so we've talked about with any. There you go. Okay, a recursive equation is an equation that states the first term in a sequence and how to find the next term. So it's just saying like how the pattern changes. It's adding 5. It's multiplying by 10. It sounds so easy, okay? It tells you a term, and you just have to say what gets you the next term, okay? So back to the problem at hand. The first thing that you want to do with a recursive is to write like what's called a reference point. And that's usually like f of 1. And I'll explain that more in a little bit, but like, what is f of 1? Like when x is 1, what's y in this problem?
4.
It's 4. Yeah, see right here? Okay, when it's 1, it's 4. Okay. Now you could have done any of these. I could have gone as a reference point, I could have gone f of 4 is 13. Okay. I could have done that. I could have done f of 5 is 10. And that just tells you like where you're starting. Okay, it's kind of like a starting point. And then here comes the tricky notation. Okay, so we're going to do f of x is equal to f of x minus 1. And then you just have to say, I'll explain that notation in a minute. And then you just have to say, like, what do we do to get the next one? What's going on in this table? How do you go from one to the other? What were we doing? We were adding 3, right? Plus 3. That's it. Okay. So let me try to explain the notation. Okay. So to get a term, we take the term before and add 3. It's going to make sense in a minute. Trust me, I've done this a few times now. Okay, I'm going to switch colors though. So let's say I wanted to get, you do not have to do this every time. All you need to do to get this right, this is the correct answer right here for the recursive. Okay. Don't think that this is all one big answer. This is just so you understand. All right. So if I wanted f of 4, okay, so I'm putting 4 in for x. That means I would take f of 4 minus 1. That's the x minus 1 right here. Okay. Plus 3. So f of 4 is equal to f of, what's 4 minus 1? It's 3 plus 3. And then f of 4 is equal to, okay, what's f of 3? So to get f of 3, I'd have to come up here and I'm like, what's f of 3? F of 3 is 10, right? Hopefully you made that jump there. So I would take the number 10 because that's what f of 3 is, and I would add 3, and then f of 4 is 13, as we can see right there. So that's just, I just proved it to show you what the notation means. But just know all that you have to do is what's in here. Okay, and if you didn't pick up on it, I think you'll pick up on it on the next one. Okay, let's just do one more thing of notes here. I'm going to erase this, so take a picture of it if you really like this pink writing here. One more, and then we're going to start the assignment. Okay, all right, so my table over here on the left, I have a new one. Okay, am I multiplying or am I adding negatives because it's going down, right? Like, what one am I doing? Explicit. What am I doing over there? Okay, see some different, ooh, a lot of people getting at the idea there. Yeah, base head divided by 2. That's my most common answer, okay? Because these are all getting cut in half. But just remember that if this is exponential, which it is, right? That means it's AB to the X. And B is, what's B? B isn't the divider, it's actually the multiplier. So Welbe is right that we're dividing by 2. What's the same as dividing by 2 but with multiplication? Someone has the answer in there. It's times 1/2. Okay, so the multiplier here is times 1/2. So 32 times 1/2 is 16. 16 times 1/2 is 8. 8 times 1/2 is 4. And so on and so forth. Okay. So my explicit should be real easy. F of X is equal to, oh, what's A though? Ooh, what's across from 0? 64. And my multiplier is what again? 1/2 to the X. Done. Okay, now we gotta do the recursive. So easy, guys. We just go F of X is equal to, and then you just kind of remember how they go. They do get a little more complex later, but for now, it just goes F of X is equal to, let's say I forgot, I'd go back up here. How does it go again? Oh yeah, F of X minus 1. So to get the next one, I take the one before it and multiply by what? What are we doing? We're not adding 3 this time. What are we doing to like each previous term? We are multiplying by 1/2 or 0.5. Okay. Okay. How many people feel okay about recursive? I don't know if anyone ever feels great about recursive, but how many of you kind of feel okay? Maybe you get it. Hit the green button if you kind of maybe feel okay about recursive. Yeah. Okay. Okay. We'll keep practicing. All right, we'll keep practicing. What time we got? We got 10:15. Half hour, guys. We're getting there. Okay. Let's click out of this and let's go to today's task. So again, if you want another breakdown of someone else showing you recursive and explicit and going into more detail too, it's a good video. Okay. It's kind of longer, but give that a shot. Okay. If you want. And then today we have today's task, which is I rule. So I think you guys have this open, but I'm gonna read it out loud and then give you guys like a couple minutes to try and answer 1 and 2, okay? All right, here we go. Marco has started a new blog about sports at Imagination High School. The mascot is the Fighting Unicorns that he has decided to call Eyesight. He created a logo for the website that looks like this, Eyesight. He is working on creating the logo in various sizes to be placed on different pages on the website. Marco developed the following designs. 1, 2, 3, 4. How many squares will be needed to create size 100? Just like yesterday, but we got a new pattern, okay? So you'll take that, type that number over there into number 1. I'll change the setting on GoFormative so you can know if you got it right or not. Hold up. There aren't many like that today though, where like you type something in and you're gonna know if you got it right or not, but this one is. So let's see here. Okay, so when you type in the correct number for number 1 now, it'll say like you got the right number in green. So let's take like 4 or 5 minutes and try to figure out 1 and 2, okay? If you're totally lost, I'm gonna go to a breakout room, Brandon or Ethan, send me a private message or let me know. That's right, Brandon. Hey, Bay, I saw you put in an answer for number 1. It is right. Did it tell you that it got it right? Oh, you just answered my question before I asked it. That is amazing. It's not showing up green or red for me. Well, shoot. Hold up. Bay, could you hit refresh and let me know if it comes up green? Oh, golly, let me check yours too. Hold on here. Yes, it did. Okay, yeah, you guys, you might have to hit refresh to see if you got number 1 right. Some people are getting it right, but they're typing in like some notation stuff. Just type in one number that's 3 digits long, and then it should tell you whether or not it's right. Okay. Okay, I'll be back in like 30 seconds, guys. If you got a question, just ask Brandon. Oh, where do I find 1.2i rule? Let me show you that. Mohammed, hold on, actually, before I leave. Just in case, I'm sure there's someone else out there who needs to see this. So 1.2i rule is, get that off the screen, is right here. You see it okay? It's just this one right there. Okay, cool. All right, Brandon, I'll be gone for 30 seconds and I'll be back. Okay, I'm back.
What do we do if we finish 1 and 2?
Yeah. If you finish 1 and 2, go try and draw what they want for number 3. Does that make sense?
Yeah.
They're just having you draw a picture. Hopefully you guys heard that too. If you're done with 1 and 2, you can just start drawing number 3. Okay, I got number 1 up on the screen. If you could stop and help us out with this one. I've heard from a few people publicly and privately that they can't seem to get the answer for number 1. Can one of you guys who did explain it? Shayna, I'll get to that one in just a second, okay? Bay, can you explain how you got your number?
Yeah, I can. So in like figure 1, for example, actually figure 2, there's 2 blocks in the center, and then there's 2 blocks on each of the 4 outer corners. And then there's always a block on top in the center and a block on bottom in the center, and that stays consistent the whole time. And then the blocks on the outer corners and the 2 blocks in the middle, with each like figure number increase, those blocks always will match what the figure number is. So I just did 100 plus 100 plus 100 plus 100 plus 100 for all of the like the center and the outer corners, and then I added 2 for the block on the top center and the block on the bottom center.
Okay, so let me see if I'm getting you correctly. If you don't understand that, there's definitely another way to do it, but I'm looking at size 3 here, right? I wish I could draw on this, but that 3 matches on the sides, right? In the middle, and then on the side, right? Like the 4 corners is like 3, 3, 3, 3, and then 3 in the middle. Is that correct?
Yeah.
And then you have like those 2 extra ones every single time, right? So what was the answer then?
I got 502.
Okay, cool. So let's do number 2. If you didn't like that way, you might like this way better. I like this way better. It's more of a math way to do it, but visual people like maybe doing it that other way. Oh no. No. How do I get out of here? Okay. Well, hold on, guys. Technical difficulties. Thanks, Brandon. Yeah, yes, it is. I'm sure the YouTube people that are going to watch this later are just loving it.
Jordan, get off my chair.
You see it? Okay. All right, I got to get rid of my abstract art here. All right, so for the table, in the picture, size 1 Was how many? What
Jojo,
was it
fuck.
for size 1? Can you guys, you there?
You're being a bad boy, Jojo.
Hold on a second. Can everybody hit mute? I'm looking for that button. I can't find it. I don't know. How do I mute everybody? Oh, there it goes. We're okay. I know there's a way to do that. It was 7? Okay. So figure 1 had 7. What figure 2 have? 12. Figure 3 had, is it just adding 5? 17. Figure 4 had 22. Okay. So obviously I don't want to carry this out to 100 because that would drive me absolutely insane, right? So that's when we need an explicit formula, so we don't have to do that. So for the explicit formula, first of all, is this linear or exponential? It's linear because it's adding 5, right? So that means it must be y equals mx plus b, where m is 5. What's b? If I go back to size 0, which doesn't really make sense in the context of the problem, but that's okay. What would be across from 0? It would be 2. So b is 2. So my explicit formula is f of x equals 5x plus 2. Okay. Now if I wanted 100, all I would have to do is take the number 100 and put it right there. And you can see that 5 times 100 is 500 plus 2 is the answer that they gave us, which is 502. That's the way I prefer to do it because I'm more mathematical than like seeing it spatially, but it's important to be able to do both. Like I can do it the other way too. They make sense either way, okay? All right, let's do recursive. This is the main new thing for the day. So showing me that you're able to do this is important. So if I have f of x is equal to f of x minus 1, what do I do? What's happening each time? How do I get the next one? Look at the table. So to get the next term, I take the one before it, and what do I do? How did I get between 7, 12, like that? What did I do? I added 5. Now, I'd probably give you like a 3 on this because you did a really good job. But what did I forget? What do I have to put on this to get the full 4, the full points? Do you remember what it was called? I'll give you a hint. Right now, I
The
have
first
no
difference?
You could add that, but to the recursive formula itself, I know I'm adding 5, but I don't know where I'm starting, right? I have no, like, where do I start adding 5? Like from what number, you know, because that doesn't mean much. I have to, from 2. Yeah, do you remember the thing called the reference point? So I have to tell myself that, okay, yeah, that's true, but in this case, f of 1 is what? So this, in other words, the first term is what? What is f of 1 here? F of 1 is 7, okay? And again, it doesn't have to be 1. I think the guy in the video says it has to be 1. You could do f of 0 is 2. F of 4 is 22. As long as you kind of know where you're adding 7 to, then you're good. All right, so for the graph over here, you could just start putting in these points like 1, 7, and then 2, 12, 3, 17, and then 0, 2. Boop, 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 boop. Description of the pattern. It's good enough for me. Good? Yes, no, hopefully. Okay. Okay. So in your next problem, it's not going to be linear. It's not going to be exponential. What do you think it's going to be? It's going to be quadratic. So for 3, they want you to draw size 4 over here in the show work section. Okay, draw what you think that would look like. Now, the whole rest of the task is done for you in this video. Okay. So the video is 10 minutes. If you promise me that you will watch it and finish the task and do your homework, I'm going to let you go. I am going to play the video in class, okay? But if you're feeling zoomed out, I'm going to let you I'm going to let you take off. But I'm going to play it in like 30 seconds, but don't take off just yet, okay? You're getting out actually way early today if you leave now. So shoot, hold on. So I just want to make sure everyone knows what the homework is. So your homework is to finish the task, okay? And then just the ready, so the 1, 2 ready. And I put in there, watch the embedded video because it is kind of tough, okay? And that's gonna tell you how to do it. But if you wanna work on your own, there's still 25 minutes left of class, but if you'd rather get off the Zoom, watch that video, you know, and do the whole thing, that's fine. But the most important video is the one that we're about to watch as a class, which is on the task right here. I'm going to play this for you in a second. So again, if you're getting off the call, go here and hit play. After you try to draw the thing first, okay? Try to draw this, okay, and then hit play, okay? So it's 9 minutes. If you want to leave, say goodbye. If you're staying, draw the thing. I'm going to play the video in like 2 minutes, okay?
Thank you.
Thank you.
Bye. Thank you.
Yeah, you're welcome. Have a good day.
I'll see you later.
See you later. Make sure to watch those videos.
All right.
Adios.
Thank you.
Yeah, you're welcome. See you later. Just make sure to watch that video that's in front of us right now.
Okay.
Bye. Thank you.
Bye-bye. Have a good one. What is the quadratic formula again? The form I like to remember is, yeah, that's pretty good. So that's the quadratic equation, right, Brandon? Quadratic formula. I think you gave her what she wanted. Like she probably wanted the quadratic formula. Remember something different. But see you, Julia. Okay, guys, we're gonna roll this video in just a second. All right, here we go. Listen up. This is our first quadratic. Okay.
Let's go through and talk about what you guys just completed on the second part of your task.
How's the video sound? Is it okay?
It's good.
It's good. Seems quiet, but okay. Hopefully you can hear it.
So, first of all, if you go through, it asked you, it said Marco decides to experiment with making his logo blockier so that it looks stronger. And so here's what he came up with. This was size 1, looked very similar to last time, but size 2, as you see, it's fatter all the way around, as well as size 3. So assuming that Marco continues with the pattern as it has begun, draw the next figure, size 4, and find the number of blocks in the figure. Okay, so I already drew this just to save a little bit of time. But what I did is I broke it up into different sections when I was drawing this. Okay, when I looked here, there were 7 different blocks. Here, once again, I broke it up into 7 pieces, but now they were 2 by 2 blocks, as you guys can see. Over here, once again, 7 sections, but now they were 3 by 3 blocks. Okay, I'm gonna finish drawing it right there. And here, I once again had 7 sections, but because it's size 4, now they were 4 by 4 blocks. And so I just have 7 4 by 4 blocks, which is how I came up with the next figure. And I'll come back to this in just a minute because it actually also helped me come up with the mathematical model. But I want to show you a few other things. Okay? Now if you look at this, I once again put together a table like I did on the first part, where it's size number, size 1, 7 squares, size 2, 28 squares, and so on and so forth. Now, here's something that's a little different. Last time when we looked at the first table, the first difference was 5. So I just found the difference between these two, it was 5. The difference between these two, it was 5. That's how I knew it was linear, because the first difference was always 5. But if you look here, the difference between these, 21. The difference between these, 35. The difference between these, 49. The difference between these, 63, and so on and so forth. They're not the same, which means it can't be linear. So I took it one step further. I knew there was a pattern, and I knew I was dealing with a whole bunch of squares, which kind of hinted me toward a quadratic because it's n by n quadratic. So I had looked at their second difference. Now the second difference is simply the difference of the differences. So the difference between 21 and 35 is 14. Difference between 35 and 49 is also 14, and so on and so forth. The second differences were all the same. Now if the second difference is the same, that means it's a quadratic function. Okay, quadratic. Or x squared. Okay, so I went through these and I figured out, I came back to this once I figured out that it was quadratic to kind of look at what I had. Once again, for coming up with an equation, if I looked right here, I had 7 1 by 1 squares. Size 1 had 1 by 1 squares. Size 2 had 7 2 by 2 squares. So this was like 7 times 1 squared. This was 7 because I had 7 squares, but they were 2 by 2 or 2 squared. Here there were 7 squares, but they were 3 by 3 squares or 3 squared. I had 7 3 squared boxes. Here I have 7 4 by 4 squares. That helped me figure out my equation right there. My equation would be f of x is equal to 7 times x squared. Okay, this size, all I had to do was figure out the size, and I squared that, and that gave me the size of each box. For the fifth one, they'd be 5 by 5 boxes, so it'd be 5 squared. And then I multiplied it by 7 because there were 7 of them. Okay? That gives me my explicit formula right here. Now I want to talk to you again about the recursive formulas. Okay, the recursive formula. Here, let's rewrite this with ends. I should just write with ends all the time. It would be f of n is equal to 7 times n squared. Okay, now the recursive formula. Once again, I had to figure out what I did to the last one to get to the next one. Okay, so I also went back to the picture for this one. I'm going to erase this a little bit. Okay. For here, well, let's erase a little bit more. There we go. Nice and quick. Okay. I once again just looked at each of those little lumps we had, because I knew they were going to be the same all the way through. So I looked at this. This one right here, it's like it transferred right here. And then I had in that square, this L-shaped that was new. Okay, I had 3 new squares here. Over here, I took my square from that one, which would be 2 by 2. And once again, left over, I had this little L-shaped here. Or 1, 2, 3, 4, 5 new squares. Over here, I would bring over this, and this part would be the same. And then I'd be left with this L shape. That would be new. 1, 2, 3, 4, 5, 6, 7. So I tried to find a pattern of how many new things I added each time. Well, to go up to this one, size 2, I noticed that if I multiplied the size by 2 and subtracted 1, I would get the number of new squares. Okay? Here, this 1 is new square. 2 times 1 minus 1 is 1. Here I had 3 new squares. 2 times 3 is 6. Sorry, 2 times 2 is 4, minus 1 is 3. And over here, 2n minus 1, 2 times 3 is 6, minus 1 is 5. 5 new squares. So if I looked, I had 2n minus 1 new squares each time. But don't forget, that was only for one box. I had 7 boxes. So I'd have to multiply that by 7. So that's how many new squares I had each time. So for my recursive formula, I could take f of n is equal to all the squares that I had before, so f of n minus 1, plus all of the new squares that I had, which would be 7 times 2n minus 1. Okay, so that's how I came up with my recursive formula. Now you also could have used this graph. This graph, if you kept going out, if you look, makes a nice parabola shape. Parabola is a quadratic, okay? So that graph could help you figure out the pattern as well as the shape of the graph lets you know it's quadratic. Now, finally, to compare the models that we developed. So, the first model we had was linear. We can look back at that. It was linear, it was straight. The first difference was the same. It was 5 each time. Okay? So, the rate of change is constant. It changed the same amount each time. The graph was a line. For a linear equation, the highest power term is x, or it's just x to the first power. It's linear. Now, exponential, I'm going to actually put quadratic here. Okay, quadratic is just a type of exponential function. Quadratic. Okay? So the rate of change was linear. Now I know that seems weird because we just said that this was linear over here. But the rate of change is this first difference. Now the rate of change wasn't constant. If it was constant, it would be the same each time. The rate of change was linear, which means the differences of each of the rate of changes was the same. So these are linear. The first differences are linear. The graph, instead of making a straight line, it's a parabola, and the highest power term is x squared. Okay? So quadratic is like taking it one step further. Now, its first differences are linear. Its first differences have all the same characteristics as the linear function.
All right, guys, hopefully that was helpful. Getting you through kind of a difficult problem. Like, it's not that hard to draw like for number 3 to draw what's next, but then getting to like think of it as 7x squared. It's kind of a different thing. All right, so that should take you through that took you through the whole task, right? It gives you everything you need. You can find it, that video again. I'll show you where it is if you don't know. So it is right here in the task, okay? So she talked about the math models for 4, and then 5, compare the models you've developed for the first few set of logos to the second set of logos. How are they similar and how they're different? So you could talk a little bit about that, and then it's task over, done. Hit submit, and then you're finished. And then the only thing you have to do is the ready. And again, please watch the video on the ready, because that is a little tricky too. But if you find yourself spending longer than a half hour, stop. Okay, shouldn't have to do more homework than a half an hour right now. Okay. So are there any questions about anything at all? Fire away out loud or in the chat.
I can't see the video on the task. It's not showing up.
Is anyone else having that problem? Can you guys not see it? Colton, did you say something? Gemma says she can't see it either. That's weird. Can anyone see it? Brandon, you can see it? Video is gone, someone says. Brandon, where is it?
I believe it was between problem 3 and 4.
So I'll show where I'm seeing it. Like I always assign the assignment myself. So here's 3, like Brandon was saying, and then it's like hanging out in space here in between the pages, and then 4. Okay, so this is it. This is what I just played right there. Does that help? Yes or no? How are we doing? I can. Those of you guys who said no, can you see it there? On my end, it's just blank space there. People are, crap. Sorry. If you can't see it, hit refresh. I can see it. Yeah, hit refresh. Still no. Can I share this thing, Brandon? Like, how would I don't know. I YouTube, I don't Vimeo or whatever. No? Nope. Okay, I will try to figure out a way, guys, to email that out to you. Yep, I will. Does anyone, maybe, hey, if you're good with Vimeo and you know how to how I could email this, stay after class. But if not, do watch the video that's for the ready, okay? Because the ready would be pretty tough without it, okay? All right, if you don't have any questions, see you later. If you want to hang out. Have a good day. Whoa, Brandon, did you just send it out? Is that the video, Brandon?
I hope.
I'm gonna copy and paste that and put it in my browser and see if it works.
It's blocked on our computers.
What Brandon sent out is blocked?
Yeah, it says like Vimeo, we can't access that site.
That's so weird that it's not there. I will try to find like another way, I guess, but I don't know if it's gonna be blocked. I can't send it, you know? Probably a Chromebook issue, could be. I'll try to figure out a way to email it, guys, if you're still here, okay? Muhammad can't see it either. BSD doesn't trust Vimeo, apparently. Yeah, I guess not. Hey, Brandon. send me your school email address, either publicly or privately, and I'm going to try emailing it to you and tell me if it's blocked, okay?
I'm not on a Chromebook. And I think that's the issue.
Is it so if they go onto something that's not a Chromebook, they'll be able to open it?
I mean, should be.
Let me stop recording this Zoom session.